Okay, this is section 7.7, video 2. In video 1, we pretty much just developed the idea and the formulas for the midpoint rule and the trapezoid rule. So now we're going to go ahead and put those to use. So our first actual example of a problem, use the trapezoid rule and the midpoint rule with n equals 5 to approximate the integral from 1 to 2 of 1 over x dx. Now obviously this is an antiderivative and integral that we can do, but we're going to use this one because it's a relatively simple one to start off with. So part A wants us to use the trapezoid rule. So we'll just say the trapezoid rule, n equals 5. And if n equals 5, that means that delta x, remember delta x is b minus a over 2. B minus a is 2 minus 1, so that's 1 over, excuse me, not over 2, over n. So 1/5 is our delta x, which is the same as 0.2, if it's easier. This will be a calculator problem. The numbers here are not going to be nice to do without a calculator. So not that it can't be done, but no point. So our trapezoid rule approximation with subintervals of 5. Remember that the trapezoids were 1/2 the sum of the bases times the height. Well, the height is constant. That's your delta x, so that's 0.2. And then the sum of the bases. I can add up base 1 and the last base, which in this case is base 5, I guess. 6, actually, base 6. Yeah, there's 6 bases because you have to count the first one. So again, it depends on whether you start with base 0 or base 1. Either way, the last base. So if I plug in 1, because that's at the first base, that will be 1 over 1, which is 1. The last base is when you plug in 2, so that's going to be 1/2. And then I have to add up 2 times the sum of all the interior bases. Well, the first one is going to be at 1.2 because you take a and then you add delta x to it. So at 1.2, so that'll be 1 over 1.2 plus 1 over the next interior base, adding another 0.2 would be 1.4. And then we're going to do 1.6 in the denominator and then 1.8 in the denominator because the next one would be 1 over 2, which we've already taken care of. So that would be how we would set that up. And then from here, we're just going to pretty much plug this into a calculator. I am not going to pull out the online calculator and go through all the number punching there. Hopefully this is something you guys can do on your own. And what we end up with is about 0.69565. And that's our pretty strong approximation. I think your calculator probably will spit out more numbers than that, although maybe that's exactly it. I actually don't remember. It's been a while since I plugged this in. But that's what we get. Part B wants us to do a midpoint approximation. So the midpoints, again, n equals 5, and delta x is 0.2. Okay, none of that changes. Now remember, this is just base times height. So it's just going to be delta x. So we'll say that our midpoint with 5 here is going to be delta x, which is 0.2, times the sum of all the bases. Well, if there's 5 partitions, the bases are going to occur at the middle of all of the partitions. So each partition is separated by 0.2. So it'd be 0, 0.2, 0.4, 0.6, and so on. So the middle in between 0 and 0.2 is 0.1. Well, actually, it's, well, sorry, 1.1, 1.2, and so on. We're starting at 1. So it's going to be 1 over the middle between 1 and 1.2 is 1.1. So that's what we plug in here. It's got to be f of that value. Plus, the next one would be the halfway point between 1.2 and 1.4. Well, that x value would be at 1.3. We'll plug that in, and so on. So 1 over 1.5, 1 over 1.7, and the last one, 1 over 1.9. That would give us 5 rectangles. Then we would plug all that stuff into our calculator, and voila, we would get the approximation for the midpoint is 0.691908. As you can see, both of those approximations are relatively close to each other. And that literally is all there is to doing the approximations. Now, what good is that if we don't know how close of an approximation that is? Well, that's a good point. Again, there's this idea of error, which we're going to talk about a little bit here. We're not going to talk about how to bound the error. That'll be something we do when we get to the last chapter. But in this case, we are going to at least talk about what the actual error is. And we know we can find the error because this is an antiderivative. This is an integral that we can take. So we're going to do that in this bottom part. What is the exact integral by using fundamental theorem? Well, the exact integral from 1 to 2 of 1 over x dx. Remember, the antiderivative of 1 over x is the natural log of the absolute value of x evaluated from 1 to 2, which is going to be the natural log of 2 minus the natural log of 1. The natural log of 1 is 0, so this is the natural log of 2. That is the exact answer to our integral. We want to see how close of an approximation we had. So the idea is that the error, oops, that's supposed to be in red. Here we go. The error is the exact integral, whatever we get for that value, minus the approximation value. Okay, and there's a reason that I'm not putting an absolute value around this, because technically an error, being the distance from something, should be a positive value because it really wants to see how far away we are from the actual answer. In this case, I'm not putting the absolute value on there because whether it's positive or negative actually has a meaning to it. And I'll explain that in a second. So let's figure out what the error is in our trapezoid method. So the exact integral, of course, gives us the natural log of 2. And the approximation was 0.695635. So it's the natural log of 2 minus 0.695635. And whatever that value is the error. And that error ends up being negative 0.002488 or so. That looks like it's pretty close, right? We're within a couple of thousandths, few thousandths, something like that. So let's take a look at what the error is from the midpoint rule. So again, it's the natural log of 2 minus, let's see, the midpoint rule was 0.691408. 0.691408. And when you plug this in your calculator, it's probably important that you actually plug in the natural log of 2 minus this value, as opposed to approximating the natural log of 2 in your calculator. Don't round it. Just plug it in like it is. And that ends up being 0.001239. All right, so now what do these specific errors mean? Well, obviously they're both pretty close. It looks like actually here the midpoint error was a little bit closer than the trapezoid error. But what does it mean? So what does it mean that the error on the trapezoids is negative? Well, if you take the actual integral value, the actual value of the integral, and you subtract your approximation, and you get a negative number, that means that your approximation, or the integral value, is actually greater than your the integral value is less than your approximation. What that means is that your approximation was actually an overestimate. You really have to think about that, because normally if you just see that, oh, I've got a negative value, it must be under because negative is below. What that says, again, is that the actual integral itself, when you subtract the approximation, gives you a negative. That means that the integral itself has to be a lesser number than the approximation in order to subtract them and get a negative. That means that the approximation is over the value of the integral, so it's an overestimate. So likewise, then if you subtract them and you get a positive number, that's actually going to be an underestimate or under approximation. Okay, neither one of the two of those things is something I'm gonna like totally stress about. You definitely want to know how to find the error. Probably won't actually ask you whether it's an over or underestimate, but it's good to know. All right, so we've got one more approximation method to do, and that's what's called Simpson's rule. This rule is it's interesting because you're not using you're not using rectangles, you're not using trapezoids. Simpson's rule actually uses parabolas to estimate the curves as opposed to line segments like Riemann sums did. Everything with Riemann sums, again, were all line segments, whether they're vertical, horizontal, or some kind of a slope in between with the trapezoids. They were all line segments. This is actually going to use parabolas. I am not going to go through the proof of this one. I usually like to do things like that, but that can be found in the book. Whether those pages are accurate depends on which version of the book, whether you're looking at a hard copy or the e-copy. It could be slightly off, but it is in the section, and you can find it if you are really interested in the proof of Simpson's rule. For Simpson's rule, one of the main things is that n, or the number of partitions, must be even. So this doesn't work if we want to break something into 9 equal sections. It only works if you want to do like 6 or 8 or 10 or something like that. And Simpson's rule says, if I take the integral from a to b of some function, that's going to be approximately, the notation is S sub n, Simpson's rule of n partitions. That is equal to delta x, which can still be found the same way as before, divided by 3. Do not confuse this, because a lot of people will say, oh, it's delta x is, found by taking the ends and dividing it by 2. That is still the case. You still have to do that part, but then you still divide it by another 3. So another way to think of it might be b minus a over 6 if you want to, but I usually tell people to find it separately and hope that you all understand that. You are going to take f of x sub, and I'm going to put 0 in this case, that'll be our beginning one, plus 4 times f of x sub 1, plus 2 times f of x sub 2, plus 4 times f of x sub 3. And the pattern of 2 and 4 repeats all the way. Oops, there should not be a end bracket on that one. That pattern repeats all the way up until you get to the last couple. And it will always end it'll always end with 2 f of x sub n minus 2 plus 4 f of x sub n minus 1 plus, and the very last one will not have a coefficient other than 1, f of x sub n. So again, the pattern will repeat. It's the first and the last one have no coefficients. Everything in between, it starts with 4 times the next one, 2, then 4, then 2, then 4, then 2, then 4, all the way up to the one right next to the end, which needs to end with a 4. This is why it has to be an even amount, by the way. And then the last one, again, has no coefficient. So it's a pattern of nothing, and then it's 4, 2, 4, 2, 4, 2, all the way up to the end, and you have to have a 4 right before the last one, and then nothing on the last one. And again, I'm just going to write this down here. Delta x is still b minus a over n. So we are going to use Simpson's rule to do the same one that we just did, the 1 over x from 1 to 2, and we'll see how close of an approximation Simpson's rule gives us. Again, now think about this. We're using parabolas, which are already curved in nature, to approximate something which is most likely curved, some kind of a function which is most likely curved. So you would think that this would probably give you a pretty good approximation. So let's see. We got n equals 10. Delta x, let's go with green. Delta x is going to be b minus a over over 10, which is 0.1. All right, So our integral from 1 to 2, 1 over x dx, can be approximated using Simpson's rule with 10 subintervals as delta x, which is 1/10 or 0.1, over 3. And it will always be dividing it by 3. Again, that proof is in the book. So, according to our rule, it is f sub 0, or the first one, which is always going to be at the first endpoint, which is 1, so that's 1, plus 4 times, plug in the next one. Well, since delta x is 0.1, we're going to plug in 0.1, so it'll be 1 over 0.1. I'm sorry, 1.1. Keep forgetting the 1 there in the bottom was where we started. Plus 2 times 1 over, the next one will be 1.2. 4 times 1 over 1.3. And I am not going to write all of them out because I'm going to run out of room. You should still write them all out on any kind of a test or quiz. I'm just doing this to save a little space and time. I'm going to move up to the last 3 like I did before. This will be 2 times, let's see, the last one will be 2, 1.9, 1.8 is the bottom. And then 4 times 1 over 1.9, and that should be the one right before the end. If you had plugged all the ones in between 1.3 and 1.8, the pattern still holds. It'll be a 4, 2, 4, 2 all the way up. And then the last one is just 1 over 2. And then again, just be careful to plug all this stuff in your calculator correctly. And what you should get here is 0.6935150. And we can figure out the error the same way that we did before. So the error, using Simpson's rule, will be the natural log of 2 minus our value of 0.6935150. This error is very small comparatively. This error works out to be negative 0.0000028, and there's more to it than that, but that's pretty close. That is 5 zeros followed by a 28, so it's 5 zeros basically, and then a 3 if you want to round that last number up there. What is that? The tenths, hundreds, thousands, 10,000s, 100,000s, millions. That is within 3 millionths of the exact value. And again, that's negative, which means it's going to be an over approximation in this case. Again, not terribly important there. But Simpson's rule, again, it's mostly just knowing the formula, plugging it in. It gives you a very, very strong approximation in a case like this. And as it turns out, and again, this is not something that is going to be expected of you. You do not actually need to know this. It's just kind of a cool thing. That Simpson's rule is actually a weighted average of the trapezoid rule and the midpoint rule. And what it says actually is that Simpson's rule, there should be a 2 right on the bottom, of twice whatever the number of partitions normally would be, works out to be exactly 1/3 of the trapezoid rule of n partitions plus 2/3 of the midpoint rule of the same number of partitions. So you could actually figure out Simpson's rule by doing 1/3 of t sub n plus 2/3 of m sub n. It would be exactly the same thing. Kind of a cool thing. Not something I am going to put on anything, so you don't need to worry about the weighted averages. All right, that is it for 7.7. So kept that one under 20 minutes. You should have everything you need, and that should be it.